be going over problem number 45 on chapter 20, which is basically a problem based on analysis of variance section. So the problem reads, supermarkets often place similar types of cereal on the same supermarket shelf. The shelf placement for 77 cereals was recorded as well as the sugar content. Does sugar content vary by shelf? Here's a box plot and ANOVA table. And before we want to dive into the questions, we want to construct an EDA for the data. And an EDA consists of 5 parts, with the first being standard deviations. And in order to find our standard deviation, we want to open up our jump data table, which is cereal. So we open up our cereal, we're giving our charts, and here we want to analyze and fit y by x, since there are 2 variables interested in. So our sugars is our y response, since that's what we want to find out, and our shelves in our x factor. We press go. And here our information, we're given information about the 3 shelves, but it doesn't really tell us much. So in order to visualize and interpret it better, we want to go to our hotspot, display options, and click box plots, mean lines, points jittered, and histograms. We also want to use our compare densities, which is basically a glorified histogram that shows our frequencies. And now we want to find our means and standard deviation, and that is also given under the hotspot and mean and standard deviation. So here we are given the means for each shelf, standard deviation for each shelf, standard error mean, and the confidence interval for all 3 shelves. So now we look at our standard deviations, and here you can see the first one 4.5, second 4.12, and third being 3.8. And to me, it's relatively close, so that's what we can infer from our standard deviations. So now we want to look at the histograms. Looking at our histograms, shelf 1 and shelf 3 appear to be skewed. Well, shelf 1 is skewed right, while shelf 3 seems roughly approximately normal, but also skewed right, and shelf 2 being skewed left. Now we want to look at our box plots. So our box plots, you can see, are here, and we can see our box plots show no sign of being skewed, and there are no outliers. So now we want to check the test of normality. To see if the data comes from a normal population, we set up the null hypothesis as H0 is sugars have a normal distribution, and HA, alternative hypothesis, is sugars do not have a normal distribution. And in order to find the p-values for the test of normality, we go to the distribution module. So we go back to our chart, analyze distribution module, and we select sugars into our variable, into our y variable. That's sugars. Into y variable, and shelf into the by column. We press OK. And in order to, instead of scrolling down for all of them, it would be easier if you just stack it. So you go to hotspot stack. So now we can see input histograms and summary statistics for shelf sugars in shelf 1, shelf 2, and shelf 3. So in order to find the p-value for the summary of the p-value for the test of normality, we want to go to our hotspot under sugars, continuous fit normal, and then go to our new fitted normal hotspot, goodness of fit, and we are given our p-value, which is 0.02, and we want to repeat this for each level. So we go to continuous fit, normal, hotspot, goodness of fit, and you want to repeat this again for shelf 3, continuous fit, normal, goodness of fit. The p-values for shelf 1 and 2 are less than 0.05, which is 0.02, and for shelf 2, and 0.02 also for shelf 1. So we conclude that our sugars do not have a normal distribution for shelf 1 and shelf 2. But shelf 3 has a large p-value, so we can conclude that the data does not come from a normal distribution. So now the last part of the EDA is our test for unequal variances. So here we set up the null hypothesis as HO is equal to sigma squared 1 equals sigma squared 2 equals sigma squared 3. And then alternative hypothesis corresponds to HA is at least two variances are different. And in order to test the unequal variances, we go to our fit y by x. We go to our chart, analyze fit y by x. Our chart, sorry. Actually, let's just close that out. Actually, close this. So we go to our fit y by x output. And we click on the hotspot and select unequal variances. Here you will find the p-value in the Levene row. So here we will find the Levene row, which p-value corresponds to 0.5196. So with a large p-value, we will fail to reject the null hypothesis. Since we cannot conclude that at least two variances are different, so now that we have conducted our EDA, we can actually move into the problem. So part A, let me just close this, open this back up. So part A asks us what kind of a design or study is this? So this study is an observational study since the study is based on data which no manipulation of factors has been employed. So this is why it is an observational study. Moving on to part B, what are the null and alternative hypotheses? So part B asks us to state the null hypothesis and alternative hypothesis for the study. Since we want to do a test about the differences of the population means for the different shells, we will denote the null hypothesis as HO is M1, which is equal to M2, which is equal to M3, and the alternative hypothesis corresponding to this null hypothesis would be HA is at least two populations means are different. So that's part B. So part C asks, what does the ANOVA table say about the null hypothesis? Since our data has equal variances, we use the p-value under the ANOVA table or analysis of variance to get the p-value. So we go to, we don't have it, so we want a hotspot, means, and ANOVA. This is where we'll get our p-value. Select that. To get the p-value, you go to the hotspot. Okay, I already said that. If it was unequal variances, we would go to the hotspot and go to, where would we go? We would use the p-value for the unequal variances. But since it is equal variances, our p-value is 0.0013 given right here. So, which is less than the 0.0013 is less than the level of significance for our data. So therefore, we can reject the null hypothesis and prove that at least two population means are different. And that since, okay. So part D asks us, can we conclude that cereals on shelf 2 have a different mean sugar content than cereals shelf 3? Can we conclude that the cereals on shelf 2 have a different mean sugar content than cereals on shelf 1? What can we conclude? So since the alternative hypothesis only states that at least two population means are different, it isn't very helpful. It does not tell us that which one is actually different from one another. So therefore, we cannot conclude which shelf is in fact different from one another. We can't conclude that cereals on shelf 2 have different mean sugars than cereals on shelf 3, and we can't conclude that cereals on the shelf 2 have different mean content than shelf 1. So all we can conclude is that at least two are different according to our p-value and our conclusion in our null hypothesis. So part E says, to check for significant differences between the shelf means, we can use a Bonferroni test whose results are shown at the top of the next column. For each pair of these shelves, the differences is shown along with standard error and significance level. What does this say about the question in part D? So it says Bonferroni test in here, but in our stats class we've used Tukey, multiple comparisons. And in order to conduct a Tukey multiple comparisons method, we want to click the hotspot. We click the hotspot and we go down to compare means and all pairs Tukey HSD. So under the connecting levels report, it shows you the levels that have been, I'm going to go down right here. Connecting levels report, it shows you that the levels that have been ranked, it shows you the levels that have been ranked from largest to smallest by the sampling average mean. Each level has the letters next to it, and levels that are not connected by the same letter are significantly different. So here you can see ranked level 2 is the highest sample average mean, followed by level 3 and level 1. And corresponding to the levels is A for 2, and 3 and 1 share B. In context with our problem, we can conclude that level 2 is different from level 1 and level 3 because it does not share the same letters. So therefore, those are the two mean differences that differ that we stated in the alternative hypothesis in our previous problem. And if we look at the confidence interval under ordered differences, for levels 1 and 3, we can see that the confidence interval captures 0. So if you go through 3 and 1, you can see that lowest confidence, -1 and 4. So by capturing 0, it's suggesting that they are not different from one another. And since the level 2 is by itself, which is letter A, the confidence interval for 2 and 1 and 2 and 3 are all greater than 0, suggesting that they are different from one another. So that is a wrap for problem number 45 on chapter 20.